watch this at some point or watch part of it later. Or what did she say to me about fast forward me and hear me talk like a chipmunk, you know, that kind of stuff. So let's take a step back for a minute.
Okay.
And let's remember something that I think is probably more you know about complex numbers, right?
Yes.
So we have real numbers, we have complex numbers, and we have what we call the standard form of a complex number, okay?
Okay.
And that's the one that goes like this. This is, and usually we use a Z
Okay.
for this when we're talking about a specific number. Sometimes we use subscripts like Z1, Z2, Z3, okay? But it's something like A plus BI. Okay. That's the standard form of a complex number. Okay. And you learned how to add these, you learned how to subtract these, you learned how to multiply these, you learned how to divide these. Okay.
Right.
And that was and then we learned how to convert between rectangular and complex. That's the formulas that you were talking about with the x squared plus y squared equals r squared and all that. Okay. Those were all rectangular, right?
Got it.
And then we went to instead of being on the rectangular system, we went to polar coordinates.
Right. Okay.
Okay. So we went to polar coordinates. And polar coordinates, remember, instead of being on a grid like you're used to, instead of being on something that looks like this, right? We went to something that looks like this.
Right.
Okay. And when we went to polar coordinates, we had R and we had theta, remember? So we had a radius and we had an angle. Okay. Now, at this point, this is still a complex number, okay? But this is the rectangular form. What you see on the left is what we call the rectangular form of a complex number, okay?
Okay.
We have a polar form of a complex number as well, okay? And the polar form of a complex number is something like this. Now you have Z, because remember Z means usually that it's complex, so we just have a Z. And I'm going to write it like this. So R cosine, and I'm going to use my zero trick because I don't have a theta on the Zoom keyboard. So I'm going to use my zero trick here, R cosine theta. And then you have plus R sine theta. Now, we never hardly ever write it this way except when we introduce it, but we write it like this. R cosine theta plus R sine theta I. This is kind of like A plus BI, because remember that this is kind of like my X, right?
Okay.
And the sine is kind of like my Y, so I have A plus BI, kind of, right? Remember?
Right.
Is that kind of, does that ring a bell at all?
A little bit.
Because remember this. Remember the X is, I'm not trying to derive everything, but I'm trying to relate everything so that when we do the formula, you see it. X is R cosine theta, remember?
Right.
So, and when you're graphing this on the plane, this horizontal axis, what would be the x-axis, is your A. So this is R cosine theta. Y then is R sine theta. Remember? We spent a lot of time with these at some point, trying to go between stuff and do a bunch of stuff to it. But this is, okay, kind of remember that?
Yeah.
And then we got to this. This is what we call complex form. Now, we don't usually, we do a little bit shorter form of this when we do it. So typically what you'll see is you'll see something like this. You'll see R, because these both have an R, right? And what you'll see is you'll see this cosine theta. You'll see cosine theta plus I sine theta.
Right.
Okay, so typically it looks something like that, right?
Mhm.
Now, if they really want to shorten it, they might write it like this. They'll write R, and they'll shorten the cosine I sine to be this R cis, and then they'll have an angle. So sometimes you'll see it this way.
Oh yeah.
Is that kind of, this is
Yeah.
kind of background, but this isn't really formulas. It's just kind of helping you to relate this.
Yeah. No, it makes sense.
So far so good.
Yes.
Now, when you're in polar coordinates, okay, if you're in polar, we have, just like when we had rules for adding, subtracting, multiplying, and dividing in rectangular, and you learned those rules, right? We have those, we have similar rules when you're in polar coordinates.
Okay.
What you add and how you subtract, and how, which gets into subtracting the angles and figuring out which quadrants and where's the R and all that. Where Demoivre's theorem comes in is Demoivre's theorem itself, and I'll show you, we're gonna see some examples of people doing it, and we're gonna do some of this, but Demoivre's theorem itself, Demoivre's theorem relates to finding powers and roots of complex numbers. Okay,
Okay.
that's what you do. So you already know how to add them, subtract them, multiply them, divide them. So you can find powers and roots, and then you've learned how to multiply and divide them already in theory.
In theory.
Okay, but does this make sense to you, or do you?
Yes. Yeah. Well, now I know what the theorem actually does.
So I'm trying to give you like.
No, I know what you mean.
Enough of an overview so that you kind of.
No, I know what you mean, but I mean, literally, Demoivre's theorem literally meant nothing to me. She's like, use Demoivre's theorem. I'm like, and I'm looking for what? And she's like,
if you remember, okay, so if you, because think of it like this: when you were doing the regular rectangular system, you learned how to add numbers, subtract numbers, multiply numbers, divide numbers, powers, all that. So let's review something over here. Okay.
Okay.
Let's do, this is going to be complex numbers, but we're going to do them in rectangular form. Now, this is this kind of form here. This is in standard form. So Z is equal to, let's say I had, now I'm going to make this tiny bit abstract, but it shouldn't be too bad. So Z is A plus BI. And let's call this Z2. And Z2 is C plus DI. So if I'm going to add these numbers here, okay, if I'm going to add numbers in complex numbers, right, I have to add the real parts with the real parts, and I have to add the imaginary parts to the imaginary parts and put an I after it. So I have A plus C because those are the real parts, right?
Okay.
And then I do plus B plus D I. So basically I add up the real parts, which are the first two.
Okay.
And I add up the imaginary parts and put an I after it to add that, right?
Okay.
Now you learned all those rules. There's adding, there's subtracting. We did it with multiplying too. Remember when you
Right.
multiply, because then you got to worry about the I squared, right?
Right.
And
Which
when
is a
you're-
-1.
Right. And when you're dividing, you got to worry about rationalizing the denominators, right?
So you don't have a radical in the bottom.
Right. So you remember. Okay. So you learned those rules. You learned those 4 rules for adding, subtracting, multiplying, and dividing in this format, right? Now, you can also do that over here. So if you have R1 is equal to, and usually you can, well, let's do Z1 actually. Z1 is equal to some radius, and I'll make it a number to make it a little bit less abstract. So if I had 4 cosine, 45 degrees, right? Plus,
You okay, Shauna?
yeah, plus I sine 45, right? That's R1, Z1. Now, if I had Z2 is equal to 4 cosine 45 plus I sine 45, right? There's a few ways, and what they typically told you to do probably was convert this back to rectangular form and then add, right? Something like
kind
that.
of.
Right?
I'm not sure.
But my point is that just like you had here, this is complex numbers polar form.
Okay.
Okay. My point in showing you this isn't necessarily to review these. If you want to at some point, we can, but that's not my focus here. What I'm trying to get at is you learned the 4 basic operations here. And you learned the 4 basic operations over here. Adding, subtracting, multiplying, and dividing.
Right.
Numbers over here, right?
Right.
It turns out that if you want to take roots of complex numbers. So let me show you an example. We're gonna go over it, but we're not gonna do this right now. If I wanted to take a root or a power, let me show you this. Okay, this is an example. So let's say I had this complex number, 2 minus I, the complex number 2 minus I to the 8th power.
Okay.
It turns out, now one way I could do this would be to write this out 8 times and multiply a whole bunch of stuff together. I would literally have to be foiling and foiling. That's not a good way to do it.
Okay.
Do it, right?
Okay.
It turns out that if you want to take a complex number to a power or a root, Demoivre's theorem is better.
Okay.
And so Demoivre's theorem says something slightly different for a power like this question as it does for a root or an angle. Okay.
Okay.
So that's what this is for.
Okay.
All right. So I'm going to show you this example because if you're doing powers, powers is not as hard in my opinion as doing the roots. The roots are a little bit more, there's a little more to it than that. Okay. what you do when you want to take a complex number to a power is, and I tried to break this down for this is not your work. This is work I did for somebody else, okay?
Okay.
What you have to do is you have to identify, notice I wrote the form, A plus BI. You have to know what A is. You have to know what B is. Why do we need that? Because we need to know R and we need to know theta, okay?
Okay.
If, now this is only if, because it depends on how they give it to you, okay?
Okay.
This is the first thing that you want to take note of. If you are trying to take a complex number that's in a form like this to a power, or if you want a root of it, like the fourth root or the fifth root or whatever, you
Okay.
need to put it in polar form first.
Okay.
This is imaginary, it's not polar.
Right.
Does that make sense to you?
Yeah.
Okay, so I'm identifying A here and B here, right? I have to get R. So R squared is A squared plus B squared. And then R squared. Now, I could have just put this under the radical and done it, but I tried to work it all out.
Yeah, yeah.
Okay. R is the square root of 5. Okay.
Okay.
Theta is the inverse tangent or the arctan. If you're more used to arctan, you can write arctan here, but this is tangent inverse. It's the same thing.
Yeah.
Okay. Tangent inverse B over A. So B is, in this case, B is -1.
Got it. Okay.
A is 2. So we have the tangent inverse of a negative. I'm sorry, we have, yeah, -5. Now, if you put that in your calculator, or you use a table, you'll see that this is about 464. Okay.
Okay.
Now remember, this is really important. Second thing I'm going to take note of, make sure that your calculator is in
Then
radians.
you, oh, radians. Okay.
Sure it's in radians when you do this.
Okay.
So now this 0.464 is in quadrant 1. Okay, now how did I know that? Let me go back, because it might have been a minute since the trig, and this gets people sometimes. Remember, we have our, this still holds no matter what system we're in. Remember, this is 0, right?
Right.
This is pi over 2 up here.
Mm-hmm.
Okay. Now, if you take 3.14, which is pi, and you divide that by 2, you get about, roughly, you get about 0.57, 1.57 when you do that. Okay. This is pi over 2. Okay. Now, the reason I'm doing this as a decimal is because you're going to get a decimal out of here. And I want you to know which quadrant you're in, because that matters for your power and for your calculation later. You have to know which quadrant this is in. You have to know which quadrant this angle's in, so you know what to do with this later. Okay, that's why I'm going over it. Now, this is pi. We know what this is as a decimal. We just had Pi Day, so we know
3.14.
Einstein's birthday, 3.14 right here.
Wait, actually?
Mm-hmm.
That's cool.
Yeah, and then the other one, this is 3 pi over 2, so this is 3/2 pi. This is about 4.71. If you don't remember, you can poke this in and find it, but it's kind of helpful to know what this is. Now, if I know that this angle is in quadrant 1, isn't it? Because it's 0.4. So the angle they're giving me is in quadrant 1, but I have a problem with that. Look at your number here. Okay, look at your number here. this is 2 minus I.
Mm-hmm.
So this is actually, if I'm going to graph it, this is actually the point 2 and negative 1, isn't it?
Okay, so that's quadrant 4.
2 and, well, 2 and negative 1, let's look here. So 2 would be somewhere here, right?
Mm-hmm.
And negative 1, I'd be down here, wouldn't I?
Right.
Now, so I need to be, here's the deal. I need to be over here in this quadrant.
Right.
But what the tangent has given me is the angle
In the quadrant 1.
in quadrant 1, which is this angle
0.46.
here.
Okay.
It's giving me, so what theta is giving me is this angle here. This is what this theta is. Okay, so it's giving me this. I don't want that. I want the angle down here, quadrant.
Right. Okay.
Does that make sense to you?
Yes.
Now, so theta is now, how do we figure this out? I need, and actually, you know what, I think I did, now that I'm looking at it, because I'm looking at my number was supposed to be -2, so this should be, yeah, I made a typo here.
Oh, okay.
It's at the, yeah, I made a typo. This should be a -2 minus I. That should be.
Oh, okay.
So my angle should actually be, because I did it correctly down here. I did this correct.
Okay.
But I didn't write these, this should be a negative number. This A should be.
So I was going to ask about that, but.
No, there's a typo there. So this actually should be, this angle is in quadrant 1. Okay.
Mm-hmm.
So that's, but what I need is the angle that's in
Quadrant 3.
3. I need the angle that's over here. Okay. So what I do, I need this angle. I need that one, right?
Okay.
So what I'm going to do here is I'm going to add pi to this. Now, why am I going to add pi? Think about this, all right? So if I'm, let me erase this. Let me erase that. So now, this is going to be, here's my, I need this angle right here, okay?
Mm-hmm.
What I have is this one.
Okay.
So let's do something here. Let me go and open I think I have to open my calculator first. I'm going to stop sharing for a second. Open up the calculator so we can actually look at the angle.
Okay.
So you can see what's going on. Okay. And we'll do one with a root as well, because I have one set up. But let me make sure that I have, okay. So let me just share the screen. Here. There's this. Okay. So now I'm going to make sure that I'm in radians. I'm going to take my own advice here. Mode. I'm in radians. That's a good sign. And I've got, okay, cool. So now I'm going to go tangent inverse. So I'm going to say tangent inverse, right? Of essentially, this is -1 over -2. Okay, because it was supposed to be 2 negatives.
Right.
It was a typo, but it was 2 negatives. It's supposed to be that. All right. So then this becomes this answer.
Okay.
Okay, that's radians. That's radians. 0.463 radians. Okay. Now, if I want to convert that to degrees, just to give you a little bit of perspective, okay, then I'm going to have to, if I have this in radians, then I'm going to have to multiply by 180. I'm going to have to multiply this by 180, and I'm going to have to then divide by pi.
Okay.
Remember that? So if I have an angle in radians, let's say, okay, so let me write this out so you kind of remember, because it's been a minute since we've done it. If you remember, okay, so we have, I'm gonna round, just not here, but when I write it, I'm gonna round it for the sake of, this is 0.463, and I'm gonna write radians next to it, okay? Now, do you remember doing, maybe this will help you, because we did a lot with this and you learned to do it really well. This is over 1, right? And now I want to make radians cancel, right?
Right. So you need a pi underneath.
Right. So I'm going to put pi radians underneath the line. Exactly. So here, I'm going to put pi underneath the line, and I'm going to call this, I'm going to call this 3.1415 radians. Right? And this is 180 degrees. Okay?
Okay.
Now, this is not necessary. This is just to give you some perspective on how many degrees we're talking about. All right.
Okay.
So we have now, what I did was I multiplied this by 180. Now I'm going to divide that answer by pi. So I'm going to go second. And let me get my mouse back first. So second pi, right? And that becomes about 26.5 degrees.
Okay.
So essentially what's happening is we have an angle that's in quadrant 1, and we are, this angle is, was I not, there it is. This angle is 26.5 degrees when I wrote it, right? So let me do that here. Let me go to my other screen share on the screen here. So this is about 26.5 degrees. Now, I don't want that quadrant 1 angle. I don't want this. Okay, I don't want this angle. I want the angle that's here.
Right.
So this angle here is 26.5 degrees. Right? So what I'm going to do is I'm going to add 180 to it. So I can find, because this is 26.5 degrees here. Right? So what I want to do is I want to find that angle. Okay. And so I add pi to it. Okay. Now, why is that? Why do I need to do that? Because here's the formula for taking a number to a power. Okay. This is an extension of Demoivre's theorem, which is taking roots. It says if you have a number that's in complex form. So all of this, okay, all of that was to get our number in the proper form So we could apply what this says.
Got it. Okay.
Demoivre's theorem, whether you're taking a power or a root, you have to be in complex form first.
Got it. Okay.
Which means you have to know what R and theta are first.
Right.
Now, if they start with R equal, then it's easier.
Okay.
You still have to do some calculation. But if you start in rectangular form up here, you've got to get into polar form before you apply the formula.
Okay.
Okay? Does that make sense to you?
Yes.
So now, what does the formula actually say to do? Well, it says if you want to take a number in polar form to a power, you take the radius to whatever the power is, whatever power. You then take the cosine, and the argument of the cosine is n. N is the power.
Okay.
Theta is the angle that you're supposed to have, not the angle that the calculator gives you necessarily. You have to make sure that your angle is actually the angle that your number is making. That's why I had to do this step first. You follow me? So I could not use the first angle. I had to use so I multiply that out, right? And all it says is I multiply the power, which is 8, right there, by the angle, and I do that twice. And then, if you work this out, okay, you take the cosine, you do this in, then you round it. Now, I think the instructions here will round it to the nearest whatever number, because this is not exact, but this is how you do that. Okay. Now that's taking a number to a power.
Got it.
That's a little easier, bully, than doing roots. It has kind of one less step, but some of these procedures are the same.
Got it. Okay.
Okay. So let's take 30 seconds, collect ourselves, breathe, stare at it for a minute. Like, let's just kind of take a step back here.
Okay.
So before we venture to the real thing that you asked about, because those things are related and they always teach them in the same section. So I'm going to show you that. We have plenty of time, not to worry. But what did we learn from this little excursion that we just took?
Well, I learned how to get R now. I know how to get R now.
Which
and I know that
the same way we got R before. That didn't change. Okay, good. What else?
I learned that N is the power that you're given when it's like in the parentheses. So I know now what N is. And then in order to get theta, you have to do the arc cosine of the I, like the number
that B over A is what it is.
Yeah, sorry, B over A.
Yeah,
and then
essentially that.
You take that.
But you got to pay attention to the quad. That's the tricky part.
And you have to pay attention to the quadrant, because you want to make sure you're in the right quadrant.
Yeah, that's the hard part. So, but the other thing, the biggest takeaway is one you didn't mention. Maybe it seems obvious, but the biggest takeaway is if you start in A plus BI form, and this applies to taking roots as well. If you start in A plus BI form, you have to get to polar first before you do any of that.
Okay, you have to start in polar form.
You have to, in other words, you might have to do a considerable 5 or 6. Now, I did because literally she was learning it. So I literally said, A is this, B is this, the tangent is this. I mean, you don't have to break it down quite as much as I did, but you do have to get R and theta.
Right.
And you do have to figure out. So if you're given that, now if you're already given a number in polar form, it cuts down on the work considerably.
Right.
But you have to recognize that, which is why I kind of went over what rectangular form is for a complex number, what polar form is for a complex number. You have to be able to recognize that.
Okay.
It's very recognizable because you'll know rectangular form doesn't look like polar form.
Right.
Right. But if you don't realize that you need to do that, then you're gonna, why can I not get the answer? And you'd be surprised how many times when you start that happens, because it's not something they say it. It's not that they don't say it to you. They say it to you. But it's not emphasized. So there's so much coming in that sometimes that filters out and people don't quite figure that out. So they go to do the first problem and they don't know what to do because they were focusing so much on
everything else
that you forgot about this first part that you have to do.
Right.
That's what happens. Okay. Is that a little more?
Yes. Have to start in polar form. Yes.
Comprehensible. So
yeah. It seems less scary.
Well, now here's the thing, okay?
Okay.
We have to think about this from an algebraic point of view. Let me review something really quick from algebra because we're gonna.
I love algebra.
We're gonna need this, and then maybe when I show you the formula for Demoivre's theorem for the actual root, maybe then it won't make sense, but maybe there'll be a rationale, because it has a lot of little, if you thought that had a lot of little components, this one has more. It's just more like a
that's the one that's like plus kn, right?
Right.
And then you have to supplement in the
right. We're gonna get there. We are, I promise you. It's just think of it like going out from a 500 piece puzzle to a 1,000 piece puzzle.
On the test that she gave us a couple days ago, she gave us, I think it was to the 4th root. And then she decided, because we only have like I think we have 15 minutes in a period. Oh. And that was like one of the last questions.
That's a lot of well, that's 5 iterations that you have to do.
Yeah, she gave it to us in the 4th root, and it was one of the last questions, and then all the kids got to it, and she was like, you know what, just set it up, because I believe you know your algebra. You wouldn't be in here.
Yeah, no, that's a lot. That's a lot of iterations. I'm gonna see if I have, but I want to review a couple of things. Maybe it might be a couple of things for you, but one thing that I have to review is, let's say that I have. Okay. Let's just say that I have this. Let me write this instead. Let's say I have X here, right? And let's say that this is a 3 here. Okay. Now, this is the 3rd root of X. Obvious, right? Every root you can write as a power. Do you remember writing this as a power? This is
X to the 1/3.
Right. This is X to the 1/3 power.
I was surprised I remembered that.
This is X to the 1/3 power. What if you saw, now, not that you're going to see this necessarily, but what if you saw this? Let's say there's a 3 here and a 4 here.
It's x to the third four or 3/4.
3/4. The
3/4?
outside number goes on the bottom, right? So this is x to the 3/4. X to the 3/4 power.
Mm-hmm.
Okay, like so. Now, why did I bring this up, pray tell? Suppose that and I'm gonna ease us into this as much as I can, okay, because I want you to understand that there's a connection here, okay? Because even students that do this for a long time, these are the little connections that can be basic and can be obvious, that if you don't get them, it makes the subsequent process even harder than it actually is. Now, we were doing powers just now, weren't we?
Right.
We were doing what we call integral powers, which means they were whole numbers, positive numbers, right? Like 1, 2, 3, 4, 5, 6, right? Mm-hmm. Well, suppose that I said to you, find all square roots of z equals 2, let's do -2 minus I. Now, I know how to find the square root of a number, right? But it turns out to be really hard to find the square root of a rectangular number like this.
Okay.
But
So
hey, square root. Can we write that as a power?
Yes.
Yeah. So could I rewrite this and say this? Could I say that if z is -2 minus I, could I say that I wanted to do -2 minus I to the power, watch this. Now, the formula changes a little bit for reasons that we'll see later. But what we're going to do is, could I say this? Could I say that? I could say it, right? -2 minus I to the 1/2 power would be the square root of -2 minus I, wouldn't it?
Right.
And we have a formula for that, don't we?
Yes.
Except now here's the problem. Here's the thing. We do have a formula for that, right? But in the formula, and this is where math can be a pain sometimes. No, we have a formula, so you were right. And I told you I wanted you to make a connection, which we are going to do. Okay. But in the formula that we did earlier, okay, n has to be, for the other format to work exactly like that, n has to be an integer power, and that's not what this is. Okay. So I'm going to see if I can find that if not, then I'll go online and show you something, because I want to show you something here. But that's the deal. And the reason why, so that formula that you saw, z to the nth power, and then r to the n cosine n theta I sine n theta, right? Remember?
Right. Yes.
That depends on n being a whole power. If it's a fraction, so if you're trying to take a root, that's where the k and the I and all those iterations come in.
Okay.
That's where that comes in. But the process is similar. Okay. The reason why you have more of them is essentially because those roots because it's complex, those roots repeat around the circle. And so those iterations are helping you find those things. But it's derived, and I don't even know the derivation off. I mean, if you ask me what is there, I would have to go look it up. Okay, I don't know the derivation of it, but it's derived from what I just showed you.
Okay.
Okay, that's why I wanted to show you that first. So you can see how that works. Now I'm gonna go look for something. So I'm gonna take a station break for a minute here while I look for something in my note.
Sounds good.
Do you have any questions about anything there?
No, I think I'm okay.
You're good? Are we feeling a little better about life at the moment right now?
Yes. Yeah. Yeah. I feel like I actually can go to my math class and do some math.
Maybe we might actually have a we might actually be able to do something. All right, let's see. Because I remember we did some, but I'm looking for something specific in my email. And if not, like I said, I can always fudge it. But I think I have something from let me see.
I actually was bragging about you, Shauna, in my math class.
Oh, really?
Yeah, because when we were doing the rose curves and stuff, I was like trying to help my teacher
Well,
out.
we had, did you show her the?
Yeah, and then she goes, "Wait, how'd you figure this out?" And I was like, "My amazing tutor." And she was like, "Do you have a tutor?" And I was like, "Yeah." And she was like, "Do you meet like in person or something?" I was like, "No, she teaches me all on Zoom." And she was like, "No way." I was like, "Yeah, she's pretty cool." Yeah, so I was bragging about you.
Well, I appreciate that. Okay, now here is, and I think I actually, this I will send you.
Okay.
In fact, this is the example of, and I'm gonna go over it, so don't worry. But I have a reason why I did this like this, because not that I won't write out the math, but it's a lot of math to write. So I wanted to give you I wanted to give you an example of this. Okay, so let me make sure that, because I want you to see this while I have it on the screen and we can go over it. So you'll have at least one example, and we'll do some more if you want, but I want you to have at least one worked example of what this looks like. Okay. So you can actually see it. And keep in mind, so don't freak out, because I did every single little.
Okay.
For the person who was learning it, okay, for their sake, I had to do every single step, because they were kind of like where you were in Trig, where she was like, oh my God, I only have X amount of days to learn it, and help me now before I, fall apart, kind of thing.
Trig.
So it was, this was in her Trig class. So what I'm gonna do is
I don't miss Trig, but I see Trig everywhere.
This is Trig, dear. So
I know. I don't miss the class, but I noticed that as soon as we started like pre-calc and stuff, like everything was reminding me of Trig, and I was like, okay, I can do this. I can do this.
Now, one thing I will tell you, okay, is that sometimes the notation in the formula, sometimes they write A, sometimes they write K, sometimes they do something different, okay? So your letters might be a little different, but I'll do my best to go through it. Okay. But at least I just emailed it to you. I replied to your acceptance, so you should see it under that. Open up the Word attachment. It's a Word document. Oh. Okay. Don't freak out, like I said, we're gonna go over it, so don't worry. Okay. Like I said, it's more I promise you, it's bad, but it's not as bad as it looks. Okay.
Okay.
It's all like the first half a page is all arithmetic. Okay. Pay very close attention to the top 1, 2, 3, about the first 8 lines up there. Okay. Pay really close attention to everything that's up there, because there's a lot of important little assumptions why that works the way it works. Okay, so we're going to go over that right now, but what I'm going to do here is I'm going to close the screen and I'm going to open up the downloads so that we can actually share the screen from the downloads. Are you looking at the because I want to open it from here so you can read it better, probably.
Okay.
Let's see. I'm going to enable editing here. Okay. Come on. Are you doing it? Okay, there it is. Now I'm gonna open up the Word because it's easier to see it on the shared screen in the Word doc. Okay.
Okay.
Now it says, let me also change the view here. I'm going to change the view. Come on, view. Okay, I'm going to zoom in. Make this, let's do, I think 125 should be good. Tell me if that looks okay on the screen. Does it? You need it larger?
No, it looks good.
Looks good? Okay. I just don't want you to be squinting when you watch this back later, because I know that was kind of small. So it says, here's the question. All right. Now, I purposely made this a little bit hard. The arithmetic is a little bit harder but the mechanics are the same. Okay. If you need to go over the arithmetic, we can. Not a problem. Find all complex cube roots, third roots, okay? Write your answers as exact values in the form a plus bi. That's what this question was, okay? Here's my number. Z is equal to -2 plus 2 square root of 3i. Now, first question. This number that they gave me is complex, right?
Right.
Is it in rectangular or is it in polar form?
Rectangular?
This is rectangular right now. If it were in polar, I would have a cosine I sine. Right. So this is rectangular right now.
Okay.
Okay. Now, here's the formula. All right. Now, in your book might have a different letter here. Some books use B, some books use N, whatever they use, okay? I used what my student's book used, which happened to be A. So, or alpha. Your book, sometimes they use a Greek letter alpha, something. Recall, so this is Demoivre's theorem.
Okay.
For roots. For nth roots. So third roots, fifth roots, sixth roots, third roots, square roots, whatever. N is the index. So if it's a third root, it's a 3.
Okay.
If it's a square root, it's a 2. If it's a fourth root, it's a 4. Okay? Here's the formula. Z to the 1 over n, because here you have the index on the outside and z is just the number to the first power, so we don't have to worry about like 2/3 or whatever. It's 1 over n. Okay, so that's why it's 1 over n and not k over n or something like that. All right, here's the formula. R. Now, this is going to look similar to what we just did.
Right. I was noticing that.
So instead of r to the n, we have r to the 1 over n.
Right. Okay.
This is where things get interesting. Because this we have to do some work with. Cosine of a or alpha plus 2k pi, and I couldn't really write out pi very well, so I just wrote 2k pi, right, over n. So this argument plus I sine alpha plus 2k pi over n.
Okay.
That was her format. Yours might be a little different. Yours might have
it's pretty much the same.
Some different letters. Now, here's my little cheat sheet for you right here. Okay. You do not have to write this out every time you do the problem, but I want you to know what they are. You have to know what these are. N is the index of your root. So we're looking for third, it says third roots, right? So N here is we'll get to that in a minute. N is the index of the root, okay? K, because we don't have a K anywhere in here. We know what N is, we don't have K. K is the constant that takes on that number from 0 to n minus 1.
Okay.
Okay. Where the complex number, now, here's I said, watch out for this. Where the complex number, this thing here up here, Z, right, is written in the form R cosine theta, I sine theta. In this case, I used alpha. You'll see why I used alpha and not theta here, but it's
okay.
The same. So far, are you okay?
Yes.
You're good here. All right. So what is this telling me that I have to do before I can start using this formula?
You have to get them into polar, right?
I have to go to polar, exactly. Which is what the next third of a page is about.
Okay.
Is getting us from this number that they gave me right here to a polar form.
Got it.
If I need a polar form, I need two things. What are they?
Wait, can you say that again?
Sure. If this number you told me was in rectangular form, the number that I started with, right?
Right.
You said, and you're correct. So this number here is in rectangular form.
Right.
I need it to be in
Polar
form down here.
Okay.
What do I need from this number to get to polar form?
The A and B?
I need to identify what A and B are. That's true. Because if I don't, then I can't get what?
The R?
Right. Technically, what I was looking for you to say, and A and B is correct, but really it's not A and B that I need because technically I have those. If I can recognize what they are, I have A and B already. What I don't have is R, and I don't have theta, do I?
Oh.
Now you're right. I need to identify A and B to get R and theta. So you weren't wrong. I was just trying to get, does that make sense to you?
Yes. Yeah.
So far we're okay.
Yes.
So far we're okay. All right. So like I said, we're going to ease into this. Okay. So here's my number, right? And we're going to go down to this line here. Okay. Now this is in the form A plus BI, right? Don't let the part of why I wanted to do this is I wanted to make you aware, and I wanted to make my students aware that you don't have to have positive numbers.
Right.
So A is the real part, the one without the I attached to it. A is -2. A can be negative, it's still real. This is still a real number, right? B is the coefficient of I. Okay. You know that from A plus BI form. Are you okay here?
Yes.
Okay, now, next thing. We're going to do some arithmetic, some algebra to get R. Okay? You can put this all under the radical, square it, and do all that. Okay? I did it separately for her because she wasn't. You can certainly put this all under the square root and get the answer at the end. I did a lot of intermediate arithmetic steps in here. So do as many of these as you need to do to get R. The formula that you're using is R is equal to, here I said R squared is equal to A squared plus B squared. So R is the square root of this. So all you're doing is squaring A, which is not hard, but watch the sign. That's the first place to trip up. You're squaring the sign as well, okay? And then squaring this, be careful of squaring your root because you need to do that.
Right.
So R squared is -2. Notice I put it in parentheses, squared, plus 2 square root of 3 squared. Okay. I simplify for a while. Okay. -2 times -2, 4. Not so hard, right? This might be a little harder. 2 square root of 3 times 2 square root of 3. 2 times 2 is 4. If I'm under the radical, I can multiply numbers under the radical, they stay. So 3 times 3, 9, still under the radical at this point. The square root of 9 is 3, so this is 4 times 3, which is 12. R squared is 16, that makes R 4. Okay.
Got it.
So R, and remember, R is positive in this form. Okay. So we take the R. Are you okay with how I got that?
Yes.
You're okay here. So I need R and I need theta. Now this is where it gets exciting, right? So
I love it.
Now, keep in mind now, this is another place where things get to be a little interesting. Because remember, we're looking for our theta, but this is not our theta yet. This is our alpha. Because we're going to need that placeholder. And that's where this is going to get the arithmetic in here. It's not hard. You just have a lot of numbers to keep track of. That's why I wrote everything out. Okay. You do not need to write it out in this degree of detail, but I'm writing it for the student who has never. So feel free to shrink this detail as you go, but I wanted you to be able to follow, and I wanted her to be able to follow what was going on. So tangent inverse, right? Now, tangent inverse, I didn't write the formula here, but I did give you the expression. This is B over A, right? So we have 2 square root of 3, -2. Okay. Where did that come from? That came
from A and B.
Yeah, this is B on top and A here, right? Then I simplify this. This is negative square root of 3. Now, this expression, if you evaluate this expression, will produce an angle in quadrant 4. Now, how did I know that? Well, if you think about, remember my A is like my X coordinate. So my A is, I have this is B over A, right? So I'm looking at negative square root of 3, right? This is an angle in quadrant 4 if I do this. Tangent inverse negative square root of 3. Okay, so if you want, let's go back, let's show you this so you can see it. So here, And I know you're not allowed to use, I just want you to see it so you understand what's going on. So here, I'm going to say, this is going to be, can you see my calculator on the screen? All right, so we're going to go with this. We're going to say second tangent inverse. Then you're going to say negative square root of 3. Second square root 3 like this. Okay, and then this is going to be, now keep in mind this is going to be in radians. Okay, so I hit enter here and I get negative 1.04. Now, if you remember, now negative means that if we have to pull out all of our, on a problem like this, you got to pull out all your skill. They all come in handy. Now, remember, this was 0, right? But this time, I'm counting the other way because it's negative. So I'm going, instead of going this direction, I'm going
clockwise
the other way, right? So now, this is, instead of being 4.71 down here, this is actually, this is going to be negative pi halves. So this is going to be negative 1.57.
Okay.
This is going to be negative, this is going to be negative pi, right? So this is going to be negative 3.4. Negative 4.71 would be up here. Okay, now the reason I bring that up is we have negative 1.04. That's over here. That's in quadrant 4 right here. Okay. My angle, my number, if you remember, is not in quadrant 4.
Right.
It's in quadrant 2. It's over here.
Okay.
Because A is negative. So this is negative and Y is positive. So my number is over here, but the calculator is giving me this reference angle in quadrant 4.
Got it.
Makes sense? Now, what I have to do, so that, and I made that note for you, if you look, but I wanted you to see it so you would understand what was going on, okay? Now, this is an angle in quadrant 4. We don't want the angle in quadrant 4. We want the angle in quadrant 2. So what did I do? I added pi. To my angle, okay? Now, this is a fundamental angle, so I gave it to you. This was negative pi thirds, okay?
Right.
So I put it in decimal form on the calculator, but this is a fundamental angle, so it's negative pi thirds. I added pi to it, and you got 2 pi thirds, okay? So if it's not a fundamental angle, you just add pi and use the decimal, just like we did when we were finding the power. Questions about this part?
No.
You're okay here?
Yeah.
Now, this is where the magic happens.
Yay.
This is where the magic happens. Remember this formula up here? Let's go back.
Okay.
Let's scroll up. In your case, move your mouse, I guess. But remember our formula right here?
Yes.
This thing is it's not because my theta, I have different thetas, right? Because I'm going to have different iterations. What I just found was my alpha.
Okay.
What I just found was this portion here. Okay.
Okay.
So I'm going to have a different iteration of this because remember my k takes on values from 0 to n minus 1, right? So let's go back down and let's see. So now this is my alpha. So now it's just, all this is now, you've done all the hard grunt work.
Okay.
You have R, you have theta.
Is it just now arithmetic after this?
It's all, well, and a little bit of trig because we're going to need to find the cosine to simplify to get our decimal. But yeah, basically it's all nasty arithmetic and a tiny bit of trig and a lot of calculating, right? So, but yeah, because here's my formula. There it is. Z is equal to 1 over, and I wrote it for you here so you can see it. Z is equal to 1 over n is equal to r to the 1 over n times the cosine of alpha plus 2k pi over 3. Now, where did the 3's come from?
They came from the n.
They came from the n, which is 3, because we were doing third roots. It seems like a half hour ago that we read that, but we were doing third roots in the problem. So, and I wrote this for you. N is 3 and R is 4. This comes from the index because we're doing third roots. R is 4 came from our calculation of R early. Okay, so now you have 4. Here's 4. This is, so then I started putting stuff in place. So this is 4 here. So this R is 4 here. N is a 3 because it's third root. So 4 to the 1/3 hangs out here. And it gets multiplied by everybody, right? 4 to the 1/3 power. And then I just start cranking stuff out. Okay. But remember, I have to do a separate calculation for every value of k. So if I'm doing 3 roots, because it's third root, we start at 0. We start at 0 and we go to the second one because we need 3.
Right.
So
n minus 1.
1 and 2.
Okay.
Right. So there's always one. Okay. So there's the same number of calculations as you have powers. However, you start at 0. That's why you take 1 off.
Okay.
So if you're doing fourth roots, for example, it'll be 0, 1, 2, 3. 0, 1, 2, 3. If you're doing third roots, it's 0, 1, 2.
Okay.
If you're doing square roots, it's 0 and 1. Does that make sense?
Okay.
And that's up there in the note where it says k goes from 0 to n minus 1. Now you know why. So now we just do it. So here you have -2 plus 2 square root of 3i to the 1/3 power. Hence, that's why we had to review the algebra of writing the root as a power. Now we know why that was, right? Right. We found our R, so we're in the format. We have our angle. This is our angle that we're using, right? 2/3 pi. And I just plug in the k. So 2 times 0 pi over 3. And then this expression in parentheses repeats itself every iteration. Now, what changes is this value in the parentheses. But these, within the same expression, so when I calculate k0, these expressions are the same. Okay. Understand me? So these are the same, except one is cosine, one is sine. Okay. Follow what I mean? Yeah. So I just did, and I just do a little bit. This is 0 is usually pretty easy because you're just left with that angle divided by whatever the number down here is. So 2 pi over 3 divided by 3, 2/3 divided by 3 would be 2/9, which is where this came from.
Okay.
You don't sound too, are you okay here?
No, I mean, yeah, I think I get it. Sorry, I know that it doesn't sound confident, but I'm processing it.
Yeah, no,
little
it's a lot to, yeah, it's a lot. That's why it's here. Okay. That's why it's on screen. But you can see why I didn't want to write it all out, because it would have been
Oh, yeah.
a lot to, I would have
yeah.
done it. I would have done it, but I think it's easier to sort of go through it. And you can practice on an easy, but do that same process on it, and you can see how it works. So this is 2/3. So essentially what we're doing is this. You essentially have 2/3, right? You have 2/3 pi actually, right? But it's 2/3, and then you have something that's 0, right? So you have a bunch of stuff that's 0 over here, right? Because this here, 2 times 0 times pi, that's 0, isn't it? And you're dividing it by 3, aren't you? So 2/3 divided by 3, let's do that. 2/3 divided by 3 means that you're doing this. So remember, when you divide with fractions, you multiply and flip it on its head. So this is 2/3 times 1/3. And that's where you get 2/9 from.
You got it.
Okay. So I wrote it out. 4 1/3. This is 2/9, right? I signed 2/9, right? So I wrote it all out for you there. And I gave you now I didn't get the decimal till later. Okay, so these, I could have gone in and poked it in and done, I didn't do that until after I generated the expressions. Okay, but this is my expression right here. Okay.
Okay.
Now I have to do that for 1. The good news is, the good news is, the only thing that changes, this doesn't. All of this stays the same. This is just R. The only thing that changes is the stuff in these big parentheses. Okay.
Okay.
That's what these iterations are all about. Okay.
Got it.
So you have 2 pi thirds. 2 times 1 is 2. So 2/3 plus 2 pi. Now I didn't do the arithmetic there, but 2/3 plus 2 is 8/3. And then I divide that by 3, I get 8/9. So it's just a matter of doing this arithmetic to get that.
Got it.
Okay. I didn't do any decimals until after I had set this up for that reason. I didn't want to confuse I did the decimal last. If it's more helpful for you, you can get the decimals as you go, but I would simplify here, get to this, and then get the decimal.
Okay.
Don't try to get the decimal before that, or you're going to be in a pickle. So then the next one that we do, we have to do 2. K is equal to 2. Again, nothing changed here except what's in here. So now instead of adding 2 pi, we're adding 4 pi. 2 times 2 is 4. So 4 pi plus 2/3 pi, that comes out to 14 pi.
Okay.
3, which is 14 pi over 9, which is what you got here.
Okay.
Okay. Now at some point, let me clear this out. Use the eraser here. So Okay, let me go down and use the mouse. Here. So now what we have is we have this. Now I can go through, it said write it as the numbers in A plus BI, so I stopped here. If I wanted the decimal, I could generate those, okay? But the problem said write it in the form, it says write your answers as what? Exact values.
Okay.
So I didn't get a decimal because it wanted exact values in terms of pi. So I stopped. If you wanted decimals, you would then poke it in and put your calculator in radians, find the cosine, and do all that. Okay.
Okay.
That would be more calculator. You would need a calculator for that.
Right.
Okay.
Okay.
Does that help at all?
Ooh. Yeah. Yeah. It does actually.
Is there a problem that you want to see me do?
Let
Yeah.
me see.
Yeah.
Okay, well, let me get my
have a
phone.
little bit
I
of
took
time
some,
if you want to do one.
some photos of some problems she had us look at, and I got one today. My partner and I were like,
You're like, oh no,
yeah,
bad things happen when we do this.
yeah. There's that one, and then there's another one, and it's.
Did you
Have you
send
heard
me?
of Have you heard of bearing before? Like something.
Yeah,
It's
like on a plane when it says it's flying at 32 degrees west of north, and yeah,
yeah,
those
we did that like a while ago, and then I thought I got away without like knowing it fully, and
bearing problem.
yeah, well
Bearing
we got.
problems can be tricky too. Did you send me a picture or did you send me an email?
Let me send you a picture. Hold on. Let me send it to you. I'll send you the one that
That you had a headache with your partner with?
yeah, let me send you that one.
No worries.
Let's see.
You and I can work on it together, okay?
Okay.
I'll be your partner. But just tell your partner that, you're not threatening her with a divorce. You just felt like you needed some outside
Yeah.
counsel for that.
Oh, I know. I told her, I was like, you know what? I'm gonna come back and I'm gonna know this. And she was like, what? And I was like, I'm gonna just come back and know it. She's like, okay, well, you better teach me. And I was like, I will try my best. We'll see.
Refer to the video, right? Or call Shauna, one or the other, right?
These were the two problems that we were like. This one, the first one I'm sending you is the Demoivres, and then the other one was
Okay.
the two complex numbers in trigonomic form.
Okay.
That one.
No
that
problem.
one.
Let's see what we got here.
But
I
those
got
are
a
the
picture of somebody's door, but I
yeah.
can't
Hold on,
see
let me
what
zoom in a little bit more.
I can't, yeah, I can't see. It says
Let me
write
zoom
the
in here.
complex numbers, use the trig forms to find is that Z1 is
Z1, Z2. Yeah.
yeah, but I can't see what the
Here,
actual
I'll text it to you. Let me text it to you.
-3 times 1 plus I, is that what it says?
Yeah. Here. Yeah. Hold on. I'll text it to
Z1
you.
is -3. That's an interesting way to write that. Okay, 1 plus I.
Yeah.
And Z2 is 2, what is that? 2 times square root of 3 plus I. So this is 2 times square root of 3 plus I. Okay, she's not asking you to find, she's asking you to multiply the numbers together, and I'll show you that too. Demoivre's theorem has another, I thought you were finding.
There's another one. There's another one I sent you.
Okay.
Hold on. I'll take a
Oh,
better
okay.
I'll take a better screenshot of that one.
No
Here.
problem. No problem. Let me
This
show
one's
you
the
how to multiply, because multiplying them, I haven't shown you how to do that yet.
okay, because there's that one too, and I was like,
Yeah, no, I'll show you. We haven't done an example of that yet.
and we're doing quotient of that too. I'm like, oh, okay. I'm like, all right.
We can, it's not that bad, honestly.
Okay.
But now you know that you have to be in
polar
form before you do that.
Right.
Right? So that's the important part. That was a key thing to know. Maybe you didn't realize that. And maybe that was why it was partially. It's actually what I was showing you to do right now is probably the next lesson.
Okay.
After this, if you haven't gotten, if you're like, wait, I think she's ahead of me.
Yeah, well, I think our teacher teaches like a lot of things in one like go. It's like
gotcha.
So I think we definitely learned what you taught us. It's just she's backtracking a little bit and she's like, I'm gonna give you
because no, I get it. Let me show you
because
this.
a lot of the kids in my class don't get it.
No, and you can see why, because it's not the easiest, not hard, but it's a lot of detail.
Yeah, there's a lot to remember.
A lot of details. And you have to kind of break it apart into separate sections to do it. Let me do this, though. Let me go to, okay, hold on. Let me see if Demoivres theorem and SLO. Let me see which one is which, because I don't know if, no, that was I have a bunch of Demoivres theorem problems, but I just don't know which problem is which.
Well, I'm glad you know how to teach this, Shauna, because
well, it can be a little bit daunting for sure, definitely.
it's because like I don't know, because she was like, here's this formula. And I was like, okay. And then I was trying to figure out how do I get this and this. And I don't know why. Like I made it seem like in my head like it was a lot more than I don't know, like a lot more scarier than it actually is.
So what you're doing here is multiplying complex numbers in trig form.
Okay.
That's what you're doing. Okay, that's what you're dealing with. So yeah, I should have an example of that, but I can't find one right now. So let me do this because I want to show you and we'll do it because actually you know how to put these in. You know how to get them in polar form now, right?
Right.
So try doing that.
Okay.
Get yourself your R and your theta for each one.
Okay.
If you need help, I'll go over it too, but I just need work on that while I'm finding it. Okay.
Okay.
Yeah, I don't want to do that. I can already tell that I don't want to do that one. I'm going to do this one. Okay, I'm gonna move this out of the way. Now, I'm gonna show you something here. Let me put something on the screen.
Okay.
We're gonna do this together, but this is actually less hard than what we were doing. If you look at the screen, the two formulas are there. I don't know if you can read his cursive. It's kind of fancy, but the top says product of two complex numbers. Okay?
Okay.
Product of two complex numbers in polar form. Big key. That's where we are, right?
Right.
Where if you're gonna do this, you want to do this in polar form, right? So what do we need? We need R and we need theta for that.
Got it.
Which means we have to find R and theta for our numbers.
Okay.
Right? So now the nice thing about what she's done here is that she's factored out the R for you, except that it can't be negative. All right. So look at your Z1, for example, here. Z1 is, if I distribute this out so it looks more familiar to you, right? This is -3 minus 3i. Are you okay there?
Oh.
On the one that you sent me. Okay.
Yeah.
We'll come back to the formula in a second. Okay.
Okay.
I just wanted you to see the formula.
Got it.
So that you would have the formula, because it's a different one than the other two that I was showing before.
Right.
Okay. That's why I wanted you to see that. So I'm going to stop sharing this for a minute. I'll throw up the whiteboard right now. So what we're looking at is, first of all, we're looking to put this in R and theta first, right? So we're looking at this. We're looking at Z here is equal to, we have -3 times 1 plus I. So don't make this too hard. Find R and theta first. Now, if it helps you, write it out so that it looks like it's supposed to. This is -3 minus 3i. Right?
Right.
Now, you know how to get R. You remember how to get R?
Yeah. So you put them into polar, which will be -3 and -3.
So A is -3, right?
A is -3
This
and
is
B
still this is still rectangular at this point, but we're going to polar, right?
Right.
-3 and -3. I agree with that. So R squared is going to be what?
R squared is equal to A squared plus B squared.
Right. So I'll write, are you used to writing it this way? R is the square root of, does she write it like this, or does she
No, usually she writes it R squared equals to X squared plus Y squared.
Okay, we'll do
That-
that. Whatever you're used to, as long as you understand what you're writing. Okay. So this is R, whoops. Hello, let's undo that ugliness. Okay, there we go. R squared, I undid a little too much here. All right, there we go. So R squared here. I'm gonna square my A. Remember, it's negative, so I have to include that. So -3 squared plus -3 squared, right? You with me? So then, what do we get?
You get, oh my gosh, can I do this? 18? 18, right?
Correct, 18.
Oh.
Yeah, because
long.
so R is the square root of 18.
Yeah. Square root of 18.
And for right now, I'm not going to worry. I'll come back to pulling out the perfect root and writing this as a different number in a second. But this is the square root of 18 for right now. Okay. Now, how about we get theta?
Okay.
Theta is the tangent inverse, or the arctan, right? Of what?
Of -3 over -3.
And that's probably the easiest math we've done all night. What does that simplify to be? Arctan, yeah, it's -3 over -3, which is +1, right? And if you, now this is where your trig skills come in, right?
Right.
Now, which quadrant is this number in?
Quadrant 3.
This is in quadrant 3, that's correct. But my reference angle, if you put this in your calculator, it'll give you 45 degrees or pi/4. Okay. So what we want to do is we have this now. So here's my pick. You don't have to graph it. I'm just using it as a visual aid to help you. This is where your angle is. That's where your angle is. What the calculator is giving you is this thing up here, right here. Okay, so it's going to give you 45 degrees. The arctan of 1 is 45 degrees. You don't want that. You want 45 degrees in quadrant 3. So this is going to be, you're over here, you're at 180 plus 45 more, which is 225. Okay, so the angle that you want, even though this is going to be pi/4, okay, this angle is pi/4. And if you need some help with that, you can look at your unit circle, you can look at your charts, you can look at a few different places. But I don't want to spend too much time on that right now. I'm going to add pi. That's how I came up with that. Are you okay with this part? Because you have to teach this tomorrow. I want you to understand where this comes from. So this angle is going to be, this is going to be 5 pi/4 now. Okay. Remember that if you are going to add this up by hand, that you have to have a common denominator when you do this. This is 5 pi/4, which is the same thing as 225 degrees. Okay. So are you okay there?
Yes.
So data, I have my R, I have my theta.
Okay.
There's my R. Now, the other thing is, I think it's easier to keep it in this form until the end, but if you want to make this, simplify the radical, this is 9 times 2 under the radical here. So this is 9 and 2. Let me know if I'm going too fast for you, okay? 9 times 2. The square root of 9 is
3.
So this is 3 rad 2. No I, because this is the radius, okay? This is just 3 rad 2. So congratulations. You've written this first number in, you have your R, you have your theta, which we need for our formula. This is our Z1, right?
Got it.
So what are we going to write in polar form? You've got the numbers. Now, can you write it in polar form? Well, it's sometimes students balk at that. They have, and then they go, I don't know what to do. It's there already. So Z is equal to, remember, it's R cosine theta. So R is, you can use 3 rad 2. You can use rad 18. We'll use 3 rad 2 because we worked hard to get that. Here's my R, 3 rad 2, right? R, and then we're going to do parenthesis. Okay. We're going to say cosine theta. Okay, so you're going to write cosine theta. This is cosine theta, cosine. Now, what's my theta? My theta is 5 pi/4.
Okay.
Not pi/4. Okay. It's cosine of 5 pi/4. I sine 5 pi/4.
Okay.
Okay. Are you okay here?
Yes.
All right, now we're gonna do a similar process with the second complex number that she gave you.
Okay.
I'm gonna finish being a sloth and writing this on the screen because I'm writing with my finger on my mouse pad. So you're probably gonna get halfway to the answer for the other one, and I'm still gonna be here.
It's all good, Shauna.
But does this make sense now?
Yes. Yeah.
Cool. That makes me happy. 5 pi over 4. So now, what are we going to do with the second one?
We're going to put it into polar form.
Okay, what are we gonna do?
We're gonna do r squared equals to 2 radical 3 squared plus 2 squared.
Yeah, because Z2 is gonna give us 2 rad 3, right? Plus 2 rad 3i. That's gonna be fun. Now, good job. So now your r squared is gonna be, well, a is 2 radical 3, isn't it?
Right.
And b is just 2, isn't it? Okay. B is 2. We're good with that. So then r squared is equal to a squared plus b squared, or x squared plus y squared, either way. So r squared is going to be 2 radical 3 squared plus 2 squared. With me?
Yes.
Now, when I square r, when I square 2 radical 3,
that'll give us 12.
Yeah, because we did that one earlier, I think. It just so happens.
Yeah.
2 radical 3 times 2 radical 3 is 4 radical 9, which is 4 times 3, which is 12. And 2 squared is?
4.
4. So 12 plus 4 is?
16.
16. And the square root of 16 is?
4.
Yes. So r is 4. Good job. Now, how do I find theta?
It's going to be the inverse tangent of 2 over 2 rad 3.
Good job. 2. Very nice. Good job. 2 over 2 radical 3, right?
Yes.
And what does that give us? Theta is the tangent inverse of? Simplify your fraction.
It'll be 1 over rad 3.
1 over radical. Now, here's the question. This is a fundamental angle.
Uh-oh.
Okay. It's a fundamental angle. So is this angle, okay, is this angle 60 degrees or 30 degrees?
Shauna, it's 30, right?
Well, this is 1/2 divided by square root of 3 over 2. So yeah, so this is going to be 1/2 times 2 over rad 3. Good job. So it's 30 degrees. Okay. Pi over 6. But now, what do we have to pay attention to?
We have to make sure that it's in the correct quadrant.
Correct. So for Z2, what quadrant are we in?
We're in quadrant 1.
We are in quadrant 1. So guess what? We do have the correct angle this time. Okay. But that's what I want you to pay attention to.
Okay.
You have to pay attention to that. And you'll see why when we get to the formula. Okay. But so this, for Z2, we're going to write, what's my R? 4, right? 4 cosine. Now my theta is, what did we decide? 30 degrees, which is pi over 6.
Pi over 6.
So this is 4 cosine pi over 6. I sine pi over 6. Are you with me there?
Yes.
We're good there?
Yes.
Okay, so now, so now we have our
Bless you.
numbers. We have our numbers in polar form.
Okay.
Okay, so just to remind you, Z1 in polar form is 3 rad 2 times the quantity cosine 5 pi over 4 plus I sine 5 pi over 4, right?
Right.
And the second one, and we're going to get to multiplying them because you asked me how to multiply them, but we need them in polar first.
Okay.
And Z2 is 4 cosine pi over 6
plus I sine pi
plus
over 6.
I sine pi over 6. You with me?
Yes.
Okay, now let's take a detour
Okay.
to something that I showed you before. Let's take a detour to the formula over here.
Okay.
There's the formula up there.
Okay.
Z1 times Z2 is equal to R1 times R2. Now, what do I do with the angles?
You're going to add them together.
I add them up. And I add, so the arguments are the same, aren't they? All I do is multiply add my angles, right? And multiply my radius.
Okay.
That's all I have. So you did all the hard work. Okay. Now notice, I couldn't do this until it was in polar form.
Right.
Once I get to polar form, the problem is actually pretty easy, isn't it?
Right, because it's all about plugging it in.
But it's getting it to polar form. This is not even as hard as finding roots, is it?
No.
You just multiply R and add the angles together, and you're done.
Right.
So let's do that.
Okay.
You wanted to find the product, right? Didn't you?
Right.
So Z1 times Z2. Let's do this. R1 is what?
It is 3 radical 2.
Okay, so I'm going to take 3 radical 2. I'm going to multiply that by
4.
4. And then I'm going to say that I'm going to put a bracket or a parenthesis there.
Okay.
Put cosine, right?
Right.
Open up the parenthesis. What is angle 1?
It is 5 pi over 4.
5 pi over 4. And I'm going to add what?
Pi over 6.
Correct. Pi over 6. And I'm going to have plus I sine of the same.
Right.
5 pi over 4 plus pi over 6. Beautiful.
Okay.
Now just do the arithmetic. Now be a little bit careful here. Don't get carried away. 4 times 3 rad 2 is not the distributive property. It's just multiplication. So you can only multiply numbers that are not under the radical with each other.
So it's 12 rad over 2?
This is 12 radical 2. Yeah. 12 radical 2 times the cosine. Now, if I add 5 pi over 4 and pi over 6 together, I need
34 pi over 24.
Oh, okay. You did it already. Cool bean. 30 and 4. Good job. So you get 34 pi. Now I can simplify that though, right?
Yeah.
34 pi over 24. So let's simplify. What do I get when I do that?
Let's see.
Half
17 over 12.
17 pi over 12. Good job. Plus I sine 17 pi over 12.
Okay.
And that's what you get when you multiply them together.
All right. And then that's it.
That's the answer.
Wow. Okay. And
Now let me ask you this. Does she want the answer back in rectangular form, or did she tell you to leave it in polar?
She usually has us put it in decimal form.
Put it in decimal? Then what you would do in that case is you would get the cosine of 17 pi over 12. Remember, your calculator has to be in radians to do that.
Right.
Okay. So it would look something like this. Let me help you.
And then for the r, do you not multiply it?
You do. If you want the decimal form of, I mean, it depends on how she wants, you know what I mean? How far does she want you to go? Does she want you to go back out and distribute, or what? You know what I mean? So it kind of depends. Like, you could get a decimal for that, multiply it by the cosine, and get it back into a rectangular form that was a decimal.
Got it. Okay.
You understand what I'm saying?
Yeah.
So I don't know how far she wants you to go. Does that make sense?
Yeah.
You need to see
pretty far with this, huh?
Do you need to see that, or do you feel?
No, I think I can.
You're okay with that?
That'll be okay.
Now, do you want to divide them as well? She didn't ask you to divide that, did she?
No.
Okay, so not there. So that's the first one, right?
Right.
Okay, and you said you had another picture for me. Use the Demoivre theorem to find the indicator. Oh, we get to find the power. Oh, goody.
Yeah.
Okay, this is
that's the one.
Now but remember, the power doesn't require as many iterations. It just requires a lot of steps. I sent you the example. We'll go.
Right.
We probably have time to finish it, but
it
doesn't require as many iterations as the
right.
And you've already done a lot of the grunt work, so you understand what you should do first, right? Let's go back. So we're doing 1 minus, what is it? 1
minus I
1 minus I to the 8th power. Okay. So you have your example. Get the one with the power out.
Okay.
1 plus I. I'll pull it up on the screen as well, so you can look at the formula again. Let me pull it up so you can see it, because I need to. It's not as hard. What is the first thing we have to do?
We have to get it into polar coordinates.
We have to, before we plug it into some formula that we don't know how to write, right? We have to get it into polar form first, which means we have to do what?
We have to do r squared equals a squared plus b squared.
Right, so we have to know what a and b are. Very good. So a is what?
It is 1.
Right, a is 1, b is 1.
Right.
And so r squared, as you said, is a squared plus b squared, which is not hard. So r squared is what?
Rad 2.
It's going to be,
sorry,
r is rad 2.
Yeah,
r is rad 2.
Sorry.
Good job. All right, what is my theta?
Okay, your theta is going to be the arc cosine of -1 over 1, which is just -1.
Is it negative? It sure is. I wrote it wrong. Didn't kill me on the first one, but it would have killed me here. So it's the tangent inverse of -1 over 1. So that is a fundamental angle. Okay. So this is.
It is, isn't it? I know the
It's not 45, it's the other one. This is your fundamental angles in -45, right?
Yeah.
But it's 45. Which quadrant is this in?
That is in quadrant 4.
X is positive, Y is negative. It's quadrant 4. So it's, so essentially what's happening is this. See, you're doing really well. You're doing good. So this is, you're looking at this now. So this is, what you're looking at is this, okay? You have the number 1 minus I. Z is equal to 1 minus I, right?
Mhm.
So this is 1 minus I. And that means that you're down here, okay? This is a 45-degree angle here, okay? But we want the angle of this. This is negative 45. This angle is 315 degrees, okay? Or 2 pi minus pi over 4, 7 pi over 4.
Okay.
Is your, this is 7 pi over 4. Are you okay with that so far?
Yes.
All right, so now you know what your angle is, okay?
Okay.
You know what your angle is.
And we know what R is.
This is, and if you want to put it in degrees, you can. This is 315, just for your own sake, okay? This is 315 right here. 315 degrees. Now, that's my Z. We know, what is my R?
The R is rad 2.
So when I write my polar form for this, because before we can take the power, we need to write the polar form, don't we?
Right.
So we're going to say Z is equal to, we're going to say rad 2.
Rad 2.
Okay, rad 2. Remember, R is always positive. So rad 2, then you use a bracket or parenthesis. Cosine of, you can use radians, or you can use whatever she's used to. This is 7 pi over 4, or 315 degrees.
Okay.
I sine 315 degrees, or 7 pi over 4. Remember that?
Yes.
Are you okay here?
Yes.
Okay. Take a breath for a minute, because now is where we're going to start to put it in Demoivre's theorem for the power. Okay. So we need the power. So what does the theorem say? Do you remember?
It's R to the nth power cosine theta plus I sine theta.
Almost.
Okay.
R to the nth power.
R to the nth power.
And then you, okay, let me go back to where we were. You multiply n by theta, if you remember.
Okay.
So let me go back and grab that. I don't know if I have that open. No. Let me go back to my other downloads for a second. But the one that we did, let me find the root. Downloads. I think I downloaded it. Copy of the monster. No, I think I did it from my email actually. But it's, what is your n?
It is 8.
8. Very good. So R to the nth power times the cosine of n theta plus I sine n theta.
N theta. Okay. So it's cosine n theta.
And remember, what is n?
N is 8.
8, and theta is
7 pi over 4.
7 pi over 4, right? So if you multiply 8 by 7 pi over 4,
you'll get, what is that? 56 over 4. That's 14.
14 pi, right?
Yes.
Now, let me show you some, because this is something we haven't, you're doing great so far. Keep going.
Okay.
Remember, what do we have to do to the R though?
We have to square it to the 8th power.
You have to take rad 2
Oh, and then
to the 8th power.
The 8th power. Right.
So be a little bit careful. I believe in you. I know you can do that. Just be a little bit careful doing it. Okay.
Okay. Got it.
Be a little, and you can use your calculator to help you. Right.
Yeah, I'm gonna use
You should get a whole number when you do that.
Okay. Because it's even, right?
It's going to be exact. Yes.
Okay. Let's see.
It should be exact if you do it correctly.
Let's see. Calculate. Okay. Okay. Okay, now I know that's. Is it 16?
It should be 16, yes.
Okay. Okay. So 16 times cosine 14 pi.
Plus I sine 14 pi. Now here's the thing, okay? If you want to find the power, you have to evaluate that, right? So you have 16 times the cosine of 14 pi.
14 pi. Okay.
Plus I sine of 14 pi, right?
Okay.
You follow me?
Yes. So they're both going to be multiplied by 16?
Yeah, exactly.
Okay.
So now think about the cosine of 14 pi, right?
Okay.
Okay, that means every rotation of the circle is 2 pi, right?
Okay.
Do you remember what the cosine of 0 is? Cosine of 0 is
3.
You can put it in your calculator. You can put it in your calculator if you want.
I really gotta learn my
Cosine of 0 is what?
Cosine of 0? Okay. I really gotta learn my table.
Cosine of 0 is 1, right?
1.
So the cosine of 2 pi is all coterminal with that. So the cosine of 2 pi would be 1. And if you go around 7 times, it's just going to be 1, right?
Okay.
So the cosine of 14 pi
is just 1.
Is 1. So that's 6. Now, here you have, so you're going to have 16 times 1 plus something, right?
Okay.
Now think about the sign.
Okay, that's 0.
Yeah, that's 0, right? So essentially you have 16 times 1 plus 0. And what is 1 plus 0?
1.
1. So what is my answer?
16.
16, exactly.
Oh, okay.
So 1 minus I to the 8th power comes out to be a real number, which is kind of cool. 16.
That's cool. It's very it's like, it's very satisfying.
Very satisfying to get that, right? Good job. And that's how you do that.
Wow. Okay. Thank you, Shauna.
Now, one quick thing, because I know I have to go soon, but I want to show you this. If you were going to divide them, and I'm not going to do that, you can do this and then you can check your answer online if you want to do it for extra practice. But just so you know, because it's all about the formula. That's all it is. But the biggest thing, I gave you the example of the big hairy one, right? we did the root, and now you have an example of how to do the big, right? But remember that, I think I didn't close the window, but I think I moved it off the video there. So let me come back and share this screen again. Here it is. If you're dividing, right, you have to be in polar form.
Okay.
So we harped on that. We know how to get to polar form now, right?
Yeah.
All you do to divide is, instead of we multiplied, remember? We multiplied the numbers. That was the first example. If you wanted to divide them, all you would do would be take the first radius, divide it by the second one.
Okay.
And then instead of adding the arguments together,
you subtract them.
You subtract the first angle minus the second one.
Got it.
Now, sometimes you get a negative angle, and sometimes they tell you to write the angle between 0 and 360, and so you have to make it coterminal, what we call coterminal. But that's essentially what you're doing.
Okay.
Okay. So if you're multiplying and dividing complex numbers, it's easier to go to polar form first. So you go to polar form, then you apply this formula.
Okay.
If you want to take it to a power, then you do r to that power of n.
Okay.
Times the cosine of the n times the angle. And theta. Okay. And I sine n theta.
Okay.
Only if you want to do roots, like the 8th root, the 6th root, the 5th root, whatever. Only if you want to do roots, you do that fancy thing where you have to iterate a bunch of times from 0 to...
Right. And then that's theta plus 2n.
It's pi? My alpha. It's essentially alpha plus 2k pi over n.
2k pi over n. Got it. 2K
and it's on the that's why I sent you an example of that one, because that one gets to be icky. That one is but yeah. So the angle that you get, yes, it is theta, but not really, because remember the angle changes every time you iterate.
So it's alpha.
It's your alpha.
Okay.
Does that help at all?
Yeah, a lot. Thank you so much, Shauna.
I know that's a ton of information to poke in there, but now you see where it's going, right?
Yes.
So if you're using any version of this, this is not Demoivre's. Demoivre's theorem is the power and the root.
Right.
But if you're using any version of this, the assumption is that you're in polar form already.
Okay.
You're not in some A plus BI form.
Right. Okay.
A plus BI form in this context is considered rectangular. Okay. You usually think of, so that might be a little bit of confusion too. When you do when you start doing these numbers, when I start talking about, like, say 2 minus 3i, right? We start talking about this as standard form of complex number. When you think of this as complex form, and then you think of rectangular as xy, and so that's when you get to the tangent invert, right? But in this case, this is considered like a rectangular form. when you're talking about versus something like this, versus something like 4 cosine, actually 4 cosine of the, I don't know, 45, right? Plus I sine 45, something like that. That's polar. This is polar. And this thing would be considered like a rectangular form.
Okay.
Even though it doesn't have X and Y in it. You see what I mean?
Okay. Yeah.
So it's not really, but that's kind of how that fans out to be. So rectangular would have something with √2 and a something like that in there, right? But strictly speaking, you can think of this as being more of a rectangular form because you can convert it back to that.
Right. Okay.
Does that help a little bit more?
Yeah. All right.
I'm gonna save these whiteboards.
Okay.
You have the example of the root if you need it.
Yes.
We did the example of the power already. Okay. So you have kind of something to go on, and now you know the formulas for multiplying and dividing, but you have to be in polar form first.
Yes.
Okay?
Have to be in polar form. Got it.
All right.
Thank you, Shauna.
You're
appreciate
welcome,
you.
Gary. Of course. I'm gonna rush off to my other session. I will be sending everybody. I have a bunch of videos and whiteboards and stuff to render, so that'll be out hopefully late tonight. 'Cause my session tonight goes until 9:30. So hopefully that'll
don't worry about it, Shauna.
late tonight or early tomorrow. I'll make sure that if you need it, you can access it before school. If you need to cram, or your teacher needs to cram.
Yeah, she might need that. All right. Thank you so much, Shauna.
Take care.
Have a great rest of your night.
Okay, you're welcome.
Bye
now. I'm going to, yeah, I've got some time. I'm going to render this. So I'm gonna